Very good evening. This is Professor Shaktivel. Today we will look into the second task on VLSI testing and testability. The task which we are going to execute today is automatic test pattern generation for combinational circuits using parallel fault simulators. So this is going to be our topic of discussion. We will try to understand the basic concepts via the basic theory, and parallelly we will also try to do the lab task and make sure that this particular task becomes easy for you to understand. So that's what we are going to do. First, let's try to understand what is this ATPG. ATPG is automatic test pattern generation, which means we are going to generate test vectors for testing any combinational circuits. And this is more important. We are not trying to test or run this for sequential circuit, because whatever ATPG algorithm whatever we apply here is basically suitable for combinational circuits. And the mode of fault simulation which we are going to do is parallel fault simulation. Probably you might have come across there are different fault simulation techniques like serial fault simulation, parallel fault simulation, and deductive fault simulation, concurrent fault simulation. So this method is mostly on parallel fault simulation, and we have couple of simulators which are being available in online, which is free of cost, open source. So let's try to see what are the tools which we are going to use. Basically, to do this task, we are trying to look into three freely available tools. One is Atalanta, the other one is Fsim, and the third one is Hope. We will look into those three. Before that, you can just go to their website and see their whole setup would be available. Particularly if you take Atalanta tool, this tool is being available in GitHubs. So the link has been provided for you. You can go with this GitHub. Their setup for this Atalanta tool as well as Fsim, Hope, all these are available. You can go ahead, download that and install in your system. The second thing is this tool, Atalanta tool, is being developed by Virginia Polytechnic University and Institute and the State University, and the whole credit goes to that particular institute. Okay, now on what basis this particular tools has been developed? Basically, we have different algorithms starting from D algorithm, podium algorithm, and one more fan algorithm. These are some of the algorithms which are used for generating test vectors, test vector for combinational circuit. The tools, whatever freely available tools which I have mentioned over here, these are the tools which is using or which is working on the basis of fan algorithm. We will try to look into this fan algorithm in a separate video. Time being, you can understand that any combinational circuit, when a fault is being provided, you can come up with a test vector specifically targeting for that particular fault which is being occurred in that combinational circuit. And the method of simulation what we are going to follow is parallel fault simulation. Again, let me presume that you are aware of this parallel fault simulation. Of course, as I said, you have different variety of simulation: serial simulation, then parallel fault simulation, deductive simulation, concurrent fault simulation. Out of that, parallel fault simulation is nothing but for a combo logic which have, if your testing machine has a word size of W, you are expected to give W minus 1 this much amount of test vector in parallel, and the whole fault simulation can be run in one stretch, which means one will be the fault free, the other W minus 1 number of test vector or bits have been allocated for the faulty one. Parallelly, you can run that as a word. Once the simulation is being executed, the final result could be obtained at the end. I am not getting into more details on this parallel fault simulation. A separate video can be put on this. Okay, so we understand in order to execute this task 2, you are expected to download these 3 tools which are available as an open source. Now let us see, in case if you are setting up in your system, what are the basic setup you need to do. As far as our VLSI lab is concerned, we have kept already downloaded these 3 tools and we have kept in our folder. What you need to do is, we have kept 2 folders. One /temp/lab, L capital. In this we have kept the 4 folders. The 4 folders are, one is bin, the other one is Atalanta, Fsim and Hope. So inside this lab folder you will be having this 4 folders, wherein each folder holds the setup file for each and every tool. There is one more folder which you need to copy, /temp/lab_exp lab2. What do we have in this lab2? In the lab2 we have 2 folders. One is ISCOS85 and the other one is ISCOS89. What are these 2 folders consist of? This have benchmark circuits in .bench format. So roughly if you go with ISCOS85, there will be around 11 to 12 ISCOS benchmark circuit. Again if you go with 89, this basically has some combo logics as well as sequential circuits. Roughly I believe it will be having around 35 benchmark circuits. So 2 files you need to copy. One, the setup file for all these 4 tools. The other one, the ISCOS folder which has benchmark circuits of both combinational and sequential. Remember, ISCOS85 is a folder which consists of combo logic, and ISCOS89 it consists of sequential circuit. All these files are in .bench format. Clear? So these are the 2 files which you need to copy. Next, in case if you are working out of this campus environment, I want you to download and keep it in your own system and appropriately go ahead and alter the path. Next, there is one file which would have been kept in temp, or you yourself can write the CSHRC file. The CSHRC file, we have 4 comments. Out of that, one is for path which is directing towards bin, another 3 comments which is used for setting up the environment. These are the basic syntax you shouldn't change. The first one is set path. You redirect or give the appropriate path of the bin. Where is bin? Bin is available in this folder /temp/lab. In case if you would have copied in your own location, then you need to give the appropriate location where it is. Inside this lab you have VLSI_testing files. In that you have bin. Next, what are the other 3? The set environments are meant for pointing out where the tool is located. So you could see Atalanta_man. This will be located. You need to point out the folder Atalanta, and for Fsim you need to point out Fsim folder. Then for Hope you need to point out the Hope folder. Remember, what is the purpose of these 3? They are the representation, or it is used for accessing the manuals. So in case if you want to access the manual for Atalanta tool or Fsim, you can straight away go here and use this. Next, so this is what available in CSHRC. Make sure these are available before you start your experiment. The next one, what is the objective of this particular task? So to understand this, let's first go with a simple diagram. Say this is my combo logic. Let us understand that this particular point had been stuck at 0. So if this is being stuck at 0, in order to make this fault visible, the only option that is available is I am expected to give 1 1, then alone this value which has been stuck at 0 will be forced with value 1, which means activating the fault. I am giving appropriate test vector, that is 1 1 for AB for this particular circuit in order to activate this fault or sensitize this path, which means if this is being stuck at 0, if this fault want to be made visible at the other end, what I need to do is make sure this particular line comes to 1. So if I want this this particular line to bring at 1, I am expected to give 1 1 to this A and B. Fine. Okay, now I understand this fault has traveled over here, but this fault need to be brought out to the output Y. How could I do it? In an AND gate, if you make other terminal to be 1, then this particular fault will be propagated to the output terminal Y. So again, if I want to have 1 over here, the only option left out is the input C and D should be 1 1. So what I understand, if I want to detect this fault stuck at 0 at Y1 node, I am expected to give the test vector 1 1 1 1, this 4 ones. So this is my test vector which detect the fault stuck at 1 at node Y1. That's as simple as this. So what are we trying to do? Here we have a simple 3 gate and we try to figure out, assuming that here and there some fault are there. In order to capture that fault, we are trying to generate the corresponding test vector which will capture that fault. The same thing need to be done with thousands of gates, and we are supposed to generate the appropriate test vector for it. So this is being done by a separate tool or an algorithm, what you call it as automatic test pattern generation. The tool or the system or the algorithm which generate this test vector, you call it as ATPG generator, automatic test pattern generator. Next, this is for a single fault. Probably in the earlier class we have discussed every fault site is liable to go with 0 and 1. So after going through all fault collapse and due to equivalence and dominance, you might be having a list of fault, a fault list. Now to detect this fault, you have different method to do it. Say suppose this is my CUT, circuit under test, and you have this final list of fault after fault collapse due to equivalence and dominance. If I assume that these are my 4 inputs A, B, C, D, to test this particular circuit, I am expected to give 2 raised to the power of 4 test vector. So if I give this 2 raised to the power of 4 test vector, then I could detect all sort of fault that could happen in my network. This is called as exhaustive testing. The problem with the exhaustive testing is such a huge amount of test vector. When I am feeding that to a large combo logic circuits, then the computation required for this, the computation time, power consumption, everything is really going to be a mammoth task. Instead, we can also go with another alternate method of testing. What do you call it as deterministic test vector generation. Deterministic test vector generation. What do you mean by this? The idea here is very simple. What you need to do is, say suppose if I have 5 fault, this is the total fault list after collapsing by equivalence and dominance. So what I try to do is, I try to generate test vector targeting for only this 5 fault. So I am just generating test vector very specifically targeting for this fault list which is available in my circuit under test. This method is called as deterministic test vector generation. So this is what usually most of the ATPG algorithm does. So the role of ATPG algorithm is generating the test vector, targeting for the specific fault that could happen in my network, and make sure that the fault is being captured in my network. Okay, so we have seen two methods. One is exhaustive, the other one is deterministic test pattern generation. One more is there, what do you call it as random pattern generation, RPG, random pattern generation, which mean I generally go ahead with a series of, as far as test vector is concerned, the sequence also matters. Means, say suppose I have 2-bit test vector. So 1 0 1 1 0 0 0 1. This could be one sequence. On the other way, 1 1, then 1 0 0 1 0 0. This could be another sequence. The point which I am trying to say here is the sequence in which the test vector is being applied one after the other could also make a difference, and probably this could end up with difference in the testing power. So as a designer, the sequence under which the test vector is being applied also matters a lot. Yes, now we understand there are three methods of testing. One is exhaustive, deterministic, and random pattern generation. So coming back here to the objective of what we are going to do with this particular task, the first one is, before starting your task, you need to make sure that all your files, that is the files that you are going to use it for testing, should be available in .bench format, because using this format only the people have developed the tool for testing or for ATPG generation. So make sure that it is in .bench format. That's the first step. Then the files which we are going to use are expected to be in ISCAS 85. As I have already mentioned, you have all ISCAS 85 benchmark circuit in this particular location. Then you can generate appropriate test vectors, say n number of test vector, to detect that particular fault. We will shortly see during our lab experiments. Then the next one is, say I could create a file which is .flt file. What is this .flt file? This .flt file is the file created by me by deliberately inserting a fault at any particular node. So for a particular benchmark circuit, I can come up with .flt file wherein I would have deliberately created a fault at different nodes, and for that file I might be asking my simulator to generate the test vector. So that's also we are going to do. A set of fault created, you can create a set of faults, and that could be made as a file, and that is being given as an input, and its corresponding test vector can be generated. This is one. And fault simulation, you could simulate the circuit by giving the test vector. There are two fault simulators again apart from Atalanta. One is Fsim and the Hope. That also we will see. And there are some terminology which would have been used, like RPT, random pattern generation, deterministic random pattern generation. T is test compaction. Probably you might be aware of this compression compaction technique. In the mode of testing, what we try to say is, compaction is nothing but, say suppose I have 18 test vector. In order to reduce the size of the test vector and its corresponding response, I can go and reduce or apply this compaction technique and reduce this 18 test vector to somewhere around, say 15 or 12 test vector. So what I am going to achieve by doing so? When I apply this test compaction, the test vector gets reduced, wherein its corresponding response is also going to reduce. Thereby I am going to reduce the memory, time consumption, testing time, testing power. So all this are the benefit of test compaction. In fact, that's a great vast topic. Time being, let's understand the importance of test compaction. So now I believe what is the background in which this particular task is going to be executed. Now let's straight away go with how are we going to execute certain commands. One by one, I will go to the location by opening the tool, and let's try to visualize this. Okay, so I have just went to my location. Possibly, I believe you could see my screen. Let me increase the size. Right. So I'm just putting PWD. So I am just in my own home location. I am going to the location where I need it. So I am going to VLSI circuits, then lab. In that I am again going to lab. Lab 2. So PWD. So you can just go to your own area. This is home user data RST. This is the place, as I said, lab 2 consists of all the ISCAS files, right? Let me list out ls-l. You could see there are two folders, ISCAS 85 and 89. If you want, I will go into ISCAS 85. So let us list it out. So here you could see all this bench .bench file. So starting from this C880, C17, all this, you have a number of files. So you can explore all this for it. Similarly, you have ISCAS 89, ISCAS 89 underscore scan. Time being, you don't worry about 89 underscore scan. So we will just go on with ISCAS 85, right? So let me get out of it. So I am here. So how do we access the tools? See, first you need to change the shell. So first give the command csh, then source your .cshRC file. This is more important. So these are the two commands which you need to give. CSHRC file, as I said earlier, it consists of 4 commands. I will also open that and show you. Let me give CSHRC. If you want, I can open that CSHRC also. Let me go with, just to have lab 2, gedit, use this .cshRC. Remember, it is .cshRC. Yeah, so can you see here? So these are the 4 lines. The first line is for bin. You need to point out the bin folder. The other things are corresponding folders. This is for accessing the manual. So I'm just closing over here. Let me get back to the original location. Right. So again, let's source this Atalanta tool. Now let me come back to the original file. So these two, as I said, first use CSH and source the CSH file. Now directly you can go for this Atalanta. Now how do I use this? Let's look at the first command and let's see what is its role. The first command is for generating test vector for the file for the file c17.bench. Now this is going to be my input and c17.test is going to be my output. The command is Atalanta -t space this name you can give according to your own wish, c17.test. This .test is important, which means for the file c17.bench, it is going to generate a test vector. The test vector will be available in c17.test. Where is that c17 .bench file is located? It is located in ISCAS 85. So we have simply given this. We will go ahead and open that file. Just for the just I am trying to copy that comment so that then and there we will be using it. I don't want to go and type it. So let's go with the first comment. I am just copying. Make sure that it is not ATLAN, Atalanta, ATA. So you make sure that the spelling are correct. So let's go back to this. I am just feeding in Atalanta minus T C17 dot test is cause. Remember, whenever you run this, the C17 dot test file will keep on overwriting on that. So that's more important. So once I feed this, you come up with all this. Let's try to analyze this. It is saying that welcome to Atalanta 2.0. It is being developed by Tong. Again, it is from Virginia Tech Institute, Polytechnic Institute. Let's see what is the summary trying to give information regarding. The first one is circuit structure. It tells us the name of the circuit, that is benchmark circuit is C17, and the number of primary input is 5, number of primary output is 2, number of gates you have 6, logic level means how many level of circuit level we have it in a combo logic. There are 3 levels. If you draw this equivalent C17, you could see there will be level. What are the ATPG parameters? First thing, test pattern generation mode. Here the important thing that need to be noted is 3 things has been used. For test pattern generation, RPT random pattern generation, deterministic test pattern generation, TC is test compaction. So all this has been applied in order to generate the test vector. Limit of random pattern, this is 16 random pattern, which means it is generating the random patterns. Then the backtrack limit is regarding the fan algorithm. In the fan algorithm, we are trying to say you can go up to the depth of 10. So the backtrack limit is 10. Of course, you can increase this in order to have much more fault coverage. Then this initial random pattern generation seed, this is mainly for having, in order to generate the test vector, we need to give the initial random value so that from there it starts generating the test vector. So that is what the initial seed value is given. Possibly you will try to understand while we go ahead with the theory. Then test pattern compaction mode, we are using 2 techniques here. One is the reverse and other one is the shuffle. Reverse is, say suppose you are generating 5 test vector. 5 has been generated starting from, let's assume that 0 0 0 0 and it end up with something 101, something like that. Again, you can reverse from 101, the sequence will change. even the change in the sequence could make a difference in the fault coverage. The other one is shuffling. Instead of following that regular pattern, you can also see that could be reshuffled. So all this will make sure that the compaction mode get improved. Then number of shuffles, there have been 4 shuffles. Test pattern generation result. Let's try to analyze this. Number of test pattern before compaction is 7. Number of test pattern after compaction is only 5. Look at the fault coverage, it is 100%. Number of fault collapsed is 22. So you have the complete list of it. Then the CPU time, all those things would be 0 because this is being represented in second, because the time, this is a very small circuit, the time taken would be in picosecond, so it doesn't show over here, right? So this is what we understand. So now let us try to re-look into it. What is the command trying to tell us? This says that for the circuit C17.bench, it is going to create C17.test. So let's try to open that C17.test and see what are the test vector available in it. So go here. I'm just going on to my location, C17.test. So you could see here. So C17.test. Let's try to open this. Let's see what it is. Yeah. So what does this says? Name of the circuit is ISCAS. From this location C17.bench. Primary input are 1, 2, 3, 6, 7. Primary output are 22, 23. Test pattern and the free responses, which means this is the test pattern which involve 5 inputs. That is 1, 2, 3, 6, 7. These are the terminals on which you are giving your test pattern. And this is your fault free response, that is 1, 1. So you have this tool has generated 5 test vector for the collapsed fault, and the true response for that is this value. So the end of this command is trying to give the total list of test patterns after collapse and their corresponding true value for that particular circuit. Fault free response has been shown over here. If there is any deviation from the faulty one and this one, then obviously it will get captured. Right. So now let's go back and see what else could be done on the next command. So what is expected for your task 2? You are expected to compute this. You need to execute for 5 such benchmark circuit. Of course, the 5 benchmark circuit is of a random choice from the ISCAS 85, and you need to go ahead and generate the test vector for this. So that will be the first command. The second is generate the test pattern without test compaction. In case if I don't have test, if I don't want compaction, still you can use the Atalanta tool. The total test vector generated and after compaction both will be the same, because in the earlier case I have showed you there were 7 test vector generated. After compaction it came down to 5. Now let's try to execute this and see what is the difference which we notice. Let's go here and copy that command, because the command is simple everywhere. Atalanta, this is minus t, instead of that minus n minus t. You need to feed this. And yeah, one more important point which I would like to say is, when once you open this Atalanta tool, then none of your Linux commands will work. So if at all if you want to access the file, what you can do is parallelly you open one more window, so that you can open and see using vi or whatever. So other Linux command will not work while you are using Atalanta tool. The only thing what you need to do is you need to exit from this and then go ahead and use it, right? So Atalanta minus n minus t. So what we have used is C432 benchmark circuit. Again, the location of that is location of the benchmark circuit. This is the location, and it is going to save the file or the test vector generated under the extension .test. So let's try to execute this. So here also you could see number of test pattern generated is 71 for this particular circuit. There is no after compaction, we didn't apply compaction. So here you could see test pattern compaction mode is none. We haven't applied anything. Again, this will give information about circuit structure, ATPG parameters, then backtrace limit is 10 here as per the fan algorithm, then number of test pattern generation, then fault coverage is 99.237. Why? Because the number of aborted fault is 3, so you can't get 100%. Redundant fault is 1, so naturally you will have a fault coverage to be lesser than that. So you could notice here. In fact, you could go ahead and open that file and see that also. You can just look at the file what we have given, c432.test. c432.test should be the file. So this is the one which I generated. Let me open this. Yeah, so this is the ones. These are my primary inputs, these are my primary output, the test pattern and the corresponding free response. This is my response and this is my test pattern. Look at here, we said 71, so there could be 71 test vector which is being generated. Hope this is clear. Now let's move on with next. Right. So similarly, you need to do this for 5 such benchmark circuit for the task 2. I have just shown one. Let's move on to the next. Right. The third command is about to stimulate the fault and store the pattern under c17.test. For this, we are trying to do two things. First, you need to create a file c17.flt. FLT file is the faulty file. Right. So the same Atalanta -f, it is not -t, -f. You are supposed to give c17 fault. This is the input file, and this is also an input file. Then where do we get the output file? This is more important. The output file will be generated on the same c17.test by default. So even if you have something else c17, it will overwrite on this c17.test. This c17 or whatever the corresponding benchmark .test, it would be replacing the previous content in c17 or c432, whatever it may be, .test it will be generating. So what are we trying to do? This is more like a deterministic test pattern generation, parallel fault simulation. So I am feeding in c17.bench as my input, and in addition I am also insisting the tool where are the places you have the fault. Now the Atalanta tool should generate the corresponding test vector aiming for this particular fault. Hope this is clear. Now first let's open this file c17 fault and see what is there in that. Then we could understand how we are creating that fault. So let's go here and let us try to see what's there in the fault FLT file c17. So here is the file. Let me open that. You use command gedit. The location for this is here same c17.flt file. Let me open this. Yeah. So what is being said here is the file has, or in that file we have introduced a fault, the fault under node 23 space /1, which means stuck at 1. So first of all, let's try to understand what is this c17 file. Then we could cross compare. that we will do. So gedit, let me do dot bench. Okay, see, if that is not there, it would be creating its own file. That is more again problematic. I don't know whether it is being given as bench. Let us check here. C17. Oh, C17 is not available here. Rather, C17 is available in ISCAS 85 slash C17.bench. Let's try to see what is there in that. Oh, 1 minute. I think it is, or let me open here and show you C17.bench. You open this with so now look at this. I have just opened as a Word file, WordPad. So what you could see here is C17 is the file, total number of input, output, number of inverter, gates. Now you could see the inputs are terminal 1, 2, 3, 6, 7. They are declared as input, outputs are 22, 23. Now in the fault file, we have deliberately created a fault, stuck at one fault at node number 23. That's what you could see in the FLT file which I have created. So I want you to create your own fault file as what has been projected there. I believe you could understand. Like this, for every .bench format file, you can go ahead and generate your own faulty file, so that you could create the test fault for that particular circuit. Got it? So again, let me go ahead. So here, let me get back to this level. So C17 gedit C17.flt. So use gedit command. So here we have seen 23 space slash. In fact, if I want to introduce one more fault, I can do it at node 19 space slash 0. If I want to do, let me save this. So now this is the faulty file which we have created. This is going to be the input for the original C17.bench. Okay, now let's get back. Go here. Let's use that command for feeding in. I am just using this particular command, Atalanta -f C17.flt ISCAS, the original file. So let me go ahead and apply this on my tool. So remember, the C17 is the one now we have generated, means we have created. Two fault I have inserted. Now I am trying to run this. Yes, now this will create a problem. The problem here is when I try to open C fault in uh, Word format, then it will create a problem. So always it is better to open this as gedit format. So I'm just exiting now. The same problem you might face across. So yeah, so now what we could do is we have just given Atalanta -f c17.flt. So this is the file which we have created a fault, and this is the original file, .bench file. So for this particular fault which we have generated, it would have created the test vector. So let's see what are the content inside this. So what we could see here is, so these are the circuit details, and again all these are what we have seen earlier. Number of test pattern before compaction is 1 and after compaction is 1. Means we are trying to, this is the deterministic test pattern which has been generated to test that particular fault which we have given. So where the test pattern will be, the test pattern will be in C17. You could see here C17. Very specifically you could see this is the test pattern which generate that fault, corresponding fault which we have created for it. This is the only test pattern. In fact, you could change that corresponding test vector also. The test fault also you can change it, and correspondingly you can get different test vector for detecting that fault which you have introduced. So what we have seen here is a file need to be created, that is FLT file, and you need to have your original file. Remember, this benchmark file and its corresponding nodes should be made as a faulty one, and then you need to use it. This is -f, this is for fault simulation. So for this you would have, you would be getting C17.test as your file, which will hold all the test vector required for this particular fault which you have created, right? So for your task 2, you are requested to create 2 files in for every benchmark circuit, 2 to fault, right? In each and every file, like that, create 2 files in FLT for each benchmark circuit, 5 benchmark circuit, 10 .flt file. In each and every fault for .flt file, you need to have 2 different faults introduced by you. So that's how you need to have it, right? This is what you are requested to do for task 2. So 5 different benchmark circuit, for each benchmark circuit 5 files, .flt files. In each .flt file you need to have 2 different fault inserted by you, and for that you need to create corresponding test vector. You could create a table, what are the fault introduced by you and what are their corresponding test vectors which you has been generated. Correct. Next, the last command which we are going to use using Atalanta is this Atalanta -t. Let us try to copy that and then execute it. So the command is Atalanta -t n.test -d, this is diagnosis, is d, 2 times 2 is cos. So let's try to see what is there in this. Let's go back and try to insert this. I'm just copying this command and coming over Right. So what is this command basically used for? Let's try to have a look at it. This is deriving n test pattern for each fault, and all unspecified input are left as it is. Fault simulation is not being performed for unspecified input. The point which you need to remember here is it stores the output pattern in n.test. This is my output file. This is my input file. Now let us try to do here, execute this particular command and see what is the output on this. Go here, I am just executing this. Now of course you will be getting all this. It is same as the previous analysis, but what we are trying to do is, for this particular benchmark file C880, it would have created one output file, that is the output file should be n dot, that's the command which we were using. It should be n dot test. So this many test vector should be created for this particular benchmark. Let us see how does that file look like. Right now let us go here and open that file, n.test, right? So n, we need to find where it is, because that's the command which we are given. This is n.test. Yeah, it is here, n.test. Of course you can give your own name. N.test is here. Now look at here. So these are my primary inputs, these are my primary output, this is test pattern and fault free response. One important thing what you can notice is, you could see, say suppose this is the fault, 796 node, it is being stuck at 1, and for that it has generated two test vectors. These two test vectors is having X filling also. X filling in the sense it could be either 0 or 1. So you might be having multiple test vector. This is the test vector which is going to test this 796 node when it is being stuck at 1. So based upon the X filling, you can fill that with the zeros or ones in order to generate the test vector in a sequence to have low power testing. Similarly, look at this particular fault 619 which is being stuck at 1. For this, these are the two test vectors. So all this will list out the total number of fault. The maximum two test vector would have been generated. Now let's get back to the original command. You could see we have used Atalanta -t n.test. So this file is going to store all the test pattern which is expected to have X also in a diagnostic mode. Maximum number of test vector it is going to generate is 2. There could be some of the fault where you might not be having 2 test vector, instead you may be having only 1. That is also possible, but maximum you are going to have 2 test vector with the X fillings, and the corresponding benchmark circuit is C880.bench. For this particular benchmark circuit, it has created this n.test. Similarly, for your lab task, you can go with selecting any five benchmark circuit. For that, you create an output file with X filling. It could be 2 or 3. You can just go ahead for generating 3 test vector, 4 test vector by changing this value alone. But this is the command. You cannot do anything on -d. Don't do anything. But this is the variable. You can change this as 3 or 4 or 5, something like this. Of course, the file name also can be given by you. Do this for 5 different benchmark circuit. Yes. So with this, Atalanta tool is over. Then the next one is Fsim. What does this Fsim is trying to have? It is also one of the simulator which is used for running the parallel fault simulation. Say suppose if I am having this test, benchmark circuit C17. For this, it start generating the test vector C17.test. So very similar to the one which, remember, this C17 is also our input file. So this input, it will take the test vector in this, apply that on the C17 dot bench, and it will run the fault simulation. What you can do is you can remove some of the fault in the dot test file, and then you can run that. Say suppose the fault coverage will change based upon the test vector which you have it. Say for this particular C17, let's assume that C17.test has some 5 test vector. You can remove couple of test vector and see whether the overall fault coverage changes. Let's try to look at this. Fsim, I'm just trying to copy. Fsim is the simulator. I'm just running this on the same platform. Fsim -t C17.test. Now what I could understand is C17 will be having number of test pattern applied is 1, fault coverage is 22.725, because previously we had total number of fault as 7, but I have removed a couple of couple of test vector. So I have applied only one test pattern. So the fault coverage you look at here, it is just 22.727. Probably you can open this and see C17.test. So this is the one. See, this is the only test pattern which we have given. You can randomly go and edit this using gedit, give couple of test pattern. The initial cases for the first command, I think we have generated 7 test vector. If you give all the 7 test vector, you would be having 100% fault coverage. When you are trying to remove one by one test vector, you could see the fault coverage goes down, which means some of the fault get undetected. So now I believe you could understand the usage of this particular command. What you need to do is the same job as Atalanta, it is also doing this. Only thing, when you keep on varying the number of test vectors that has being applied, correspondingly the fault coverage also changes, but it doesn't have a special feature. It is almost same as what is being done by Atalanta 2. So that's what. So you can keep deleting some of the fault in the dot test file and then tabulate the same. What is the fault coverage you have got by having how many number of test vector. Next, possibly the next one is the Hope. This is also a parallel fault simulator. Let's try to run that using Fsim. This is the only command which we are trying to use. You can also go to their help, and I want you to explore multiple other commands. For want of time, I am just introducing only a couple of commands in that. Hope. This is Hope -t C17.test -d. Again, let me run this. Again, what you could see is the test pattern is only 1, test coverage is only 1, because previously our total number of test pattern only I had 0. I want you to change the total number of test pattern in C17 file to be 7, so that you will have a better understanding. What is the purpose of this command? Let me open and show you. So what it does, this particular task need to be done for 5 different benchmark circuit and analyze the number of fault detected by the test vector. One important thing what you can notice is this Hope will generate a log file. So you can go and open that log file and see what are the undetected fault. Let me see for this particular C17.bench, it would have created C17.test as this is my input, this is my input, and this is also my input, because this is my benchmark circuit. Using the test vector that has been generated, it is applied, and it would create a log file. Let me look at the log file. The log file would be located here. Let's go ahead and see where is the log file. C17.log. open this. So it's taking time. Yeah, so you could see here in the log file which we run using Hope, these are the test, like these are the fault which we have introduced, 5 fault detected. Again, it gives a summary about what are the details about the circuit information, number of test pattern generation, fault coverage, everything. It also tells me what are the list of undetected fault. You see here, this many, because we have reduced the test vector to 1. If you go and change the dot test file c17.test, include multiple, that initially we have generated 7 test vector. No, if you have include all that, then the number of undetected fault will go down. So the beauty about this Hope is it will give me what are the undetected fault. So that's the beauty of this. Like this, you will have a log file for each and every dot bench circuit which you are trying to run. So for this, you are supposed to go ahead with 5 different benchmark circuit and get their log file and see what are the undetected fault. Finally, if you want to get any help, no, so what you can do is simply do Atalanta -HA. But before running this command, what I want you to do is first run this set environment. We have four command lines in the CSHRC file, and the set environment for each and every tool. Suppose if you want to open the manual for Atalanta, then what you need to do is set environment man, that corresponding line alone you should run, and then you invoke this particular Atalanta command. So that's what we are supposed to do. So let me show that. With that we can wind up. Let's try to see here. So let me go to that CSHRC file. In the CSHRC file, this is the first set environment. I'm just copying this. Go back to this. I'm setting environment. Now after doing this command, then you go for help. So help command, you can just go ahead with the usage of Atalanta or anything, whatever tool, Hope or Fsim -HA. So I'm just going ahead and so you will get all the information relevant to this Atalanta tool. Similarly, if you want Hope, you can do that also. So I believe this video would have taken you through how to operate Fsim, then Atalanta tool, as well as the Hope tool. Now what are you going to do? I have said what you need to do in each and every command. Then you need to find out the fault coverage for each and every stages, undetected fault, test vectors, then creating a fault insertion file, and finally give your conclusion. There are some papers which has been published comparing Atalanta tool and Hope. One such one is this one. If you have a chance, you can download this from the IEEE website and read this. I try to put that in the Google Drive also. Go ahead. Thanks. If any doubt, you can just get back. Thanks for listening. Meet you in the next video.